Hey guys, I am going to be wrapping up the Big Bang Theory with our last slideshow today. You'll have another assignment assigned on Thursday. And with that said, I do want to jump into a couple things that I shared out last night. First of all, we are restructuring the workflow a little bit. So this is what the new weekly learning modules will look like. A couple things to note here. For Integrated Science Explorer, we've got an assignment assigned on Tuesday and an assignment assigned on Thursday. The Tuesday assignment will be due that following Thursday, and the Thursday assignment will be due on the following Tuesday the next week. Now you also have some optional Google Hangouts here. Again, these are optional. My intention behind this is say you get this assignment on Tuesday today and you start it on Tuesday, but you have some questions on Wednesday in this window, which is, let's see, an hour and a half window, then you can pop into that Google Hangout, ask your questions, say hi to me, say hi to some friends, but you certainly don't have to be there. I'm going to go into this document real quick. I posted this document in Schoology, and I just want to make sure you're aware that if you want to get into one of those Google Hangouts, all you have to do is click on the link. All of these are links, and they all go to different Google Hangout chat rooms. So if I click on the IS Explorer chat room, I'm going to go into, maybe, there we go into a Google Hangout, and what will probably happen is I will be in this during those times, but with my camera and my microphone off. And then if I hear the sound that someone's entered, I'll turn my mic and my camera back on and we can chat. But if no one's in there, I'll be totally invisible doing work and then reappear when someone is in there. All right, so with that said, let me just get that out of there. So just to clarify, this will show that you have 2 optional Google Hangouts a week, many more available at different times in the day, but these are specific for this class. So that was a piece of feedback that came from the survey was let's have some Hangouts. And then another piece of feedback was to pare down the work a little bit. So you'll only have 2 assignments a week. They might be a little lengthier because there's only 2 of them, but I think 2 instead of 5 will be a lot more manageable for myself and hopefully for you guys. So lastly, let me go back to here. There was one other piece of feedback, and that was it'd be great if we could get everything for the week right up front. Unfortunately, and I actually put my weekly schedule that I made this weekend in that Sunday night email if you wanted to check it out. But one thing I wanted to show you is that I'm actually editing and shooting these videos the day before you're watching them. So as much as I wish I could post everything for the week, right now that's just not a possibility. I've given myself, as you kind of have in the school schedule, Friday as a total flex day. So in the future, I might get caught up to the point where you see a whole week's worth of material go up at once, but right now it's not really in the table. And lastly, I'll just say that as I find myself in my own home all day, every day, staying on top of my goals means that I really need to have a schedule. So I would encourage you all to make a schedule if you haven't yet. It could really help things moving forward. So with that said, we are going to jump into the last of the Big Bang videos today. We're going to carry on from what we talked about last week with emission spectra, and we're going to move into what is called the Doppler effect and red-shifted galaxies. Here's some learning objectives for you. First of all, I'd want you to be able to describe the Doppler effect, what it is and when it occurs. I'd want you to be able to explain what red-shifted galaxies are. And then ultimately, and this will be the PD question on your assignment, is Can you evaluate how redshifted galaxies are evidence for the Big Bang Theory? Again, something that we see today in present time, redshifted galaxies, are evidence for an idea that we have about the past, the Big Bang Theory. All right, so first of all, what is the Doppler effect? The Doppler effect is the apparent change in the wavelength of a wave when emitted by a moving object. So if an object is doing two things, if an object's in motion and it's emitting a wave, then the Doppler effect will occur. And I'm going to start with some more straightforward examples before we get into astronomy. In this first example here, we have a duckling that is swimming on the water. So the duckling is in motion, it's swimming, and as the duckling is swimming, it's emitting water waves, little ripples. And what are happening to those ripples is the Doppler effect. So the waves in front of the motion, in front of the duckling, are being compressed by the motion itself, and therefore have a shorter wavelength. And the waves behind the motion, behind the duckling, are stretched and therefore have a longer wavelength. And this particular image even tries to draw some crests on there so that you can see waves in front are compressed, waves behind are stretched. That is, in essence, the Doppler effect. There's just another image of an adorable duckling. And you can see it again, although there is a lot of turbulence back behind the duckling, so it's harder to see the stretching part, but you can see the compression in front of the motion. The ripples are very close together here, and then even as you try to follow a ripple out, you can see the wavelengths getting longer as it moves behind the duckling. So where's another example that we could see the Doppler effect? This is again not in astronomy yet. We're going to just talk about sound for a minute. Sound is a wave, obviously, sound waves. And so therefore they have wavelengths. And a high-pitched sound has a short wavelength. A low-pitched sound has a long wavelength. It's nothing to do with volume. This has to do with pitch, like a note. I would sing for you, but I really don't want to. And we can observe the Doppler effect when a fire truck or ambulance speeds past with its sirens on. And you might have heard this before in your own life. If I'm in front of the ambulance as it's moving towards me, again, the ambulance is moving and it's emitting a sound wave from its siren, I'm going to see the Doppler effect. And when I'm in front of the ambulance, the waves are going to be compressed, so the wavelength's getting shorter, and therefore the pitch will sound higher. And when I'm behind, say after the ambulance has passed, the waves behind are being stretched, and therefore the wavelength is longer and the pitch will be lower. So we're going to try this this YouTube video, which is terrible video quality, but the sound works all right. And we did have some talk last semester about whether or not this was augmented, digitally altered to enhance the Doppler effect, because it is pretty noticeable here. But this is just a video of a fire truck driving by, and as it drives by, first you're going to hear it coming towards you, so the waves are being compressed. The wavelength is shorter and it's going to sound really high pitched as a siren, and then after it passes, the waves are going to be stretched, and you'll notice an almost instantaneous, when it drives by, drop in pitch to a really low pitch. So let's see how this works. That did not work. Bear with me. So in watching that, hopefully you heard the pitch change. Again, it's not the best video quality in the world, but it was the sound we were after in that fire truck when it's approaching. It certainly has a higher pitch than when it's passing and, and behind you. All right, so now let's start to get into some astronomy with the Doppler effect, now that we understand what it is. Again, it's the idea that waves in front get squished and waves behind get stretched. Um, so now we're going to obviously jump into light, because that is an astronomer's number one tool for understanding the universe is electromagnetic radiation. So, first of all, to remember that light is a wave, it has a wavelength. And when we focus in on the visible spectrum, blue light has a shorter wavelength. The blue and purple end is on the short energy, or the short wavelength, high frequency, high energy end of the spectrum. And on the other hand, conversely, red light is on the long wavelength, low frequency, low energy end of the spectrum. So it's super important here that you recognize that blue light is the short wavelength, red light is the long wavelength. These terms, blue and red, are kind of how this is all nested. So when an object, like a galaxy, is moving towards us, the light waves coming off from it are going to get squished. So the light coming off from it is going to seem more blue. It's not necessarily that it's going to be blue, but it's going to seem more blue than if that galaxy was at a standstill. So when an object like a galaxy is moving towards us, we say it is blue shifted because the wavelength of the light has been compressed, been made shorter. Again, blue shifted on the spectrum does not mean it's blue light. It just means it's shifted towards the blue side of the spectrum, the rainbow. Conversely, when an object, like a galaxy, is moving away from us, we say it is red shifted because the wavelength of the light has been stretched. It's been made larger. And this graphic does a good job summing that all up. If this is a galaxy, it's moving towards me, this eyeball. The source is moving towards the observer. We're seeing the wavelength decrease. It's becoming squished. Therefore, the frequency is increasing and the observer is experiencing blue shift. And conversely, if the object is moving away from us, so now on this eyeball, that's the source is moving away from the observer, the wavelength is increasing, it's being stretched, and the frequency is therefore decreasing, and the observer is experiencing redshift. So hopefully you can see how we explained what the Doppler effect was, and then we went from a duckling on water to sirens changing pitch as they drive by you on an ambulance or a fire truck. And now we're getting into light, and we're talking about the light that galaxies give off and how we can see a change in that light and have an understanding of, is the galaxy moving away or moving towards us? Now, you might ask, well, how do we know what the light is supposed to be, right? If we see a blue shifted galaxy, how do we know the difference between it being blue shifted or it's just a bluer galaxy than other galaxies? So that's a fair question. And the short answer is emission spectra. We're going to use emission spectra as like bookmarks. So recall that emission spectra are the specific colors of lines, excuse me, I read that wrong, are the specific lines of color given off by elements like hydrogen. And we know exactly what wavelength, what color the emission spectra of hydrogen is when at rest. So this isn't hydrogen, but let's say this is some element that we can observe in both in laboratory and in distant galaxies. We know what number this line falls at in terms of wavelength. We could mark that as, say, 500 nanometers is this line. So the emission spectra in a laboratory is giving us a benchmark of where to start. Then we can compare the position of hydrogen's emission spectra at rest to those of distant galaxies and observe if hydrogen's emission lines have been blue shifted because the galaxy is moving towards us, or red shifted because the galaxy is moving away from us. So if this is what the lines I see in the laboratory, and then I look out at a distant galaxy and I collect the light, I diffract it, and I get emission spectra lines again, when I compare them to what I see in the laboratory at standstill, I'm going to see something that is either all the same lines, same distance apart from each other, but shifted to the red side of the spectrum. So here you can see this red line right here is shifted farther down the long wavelength, the red side of the spectrum. So that red line becomes even redder with the red shift. Here we've got maybe a green line that becomes slightly more yellow with the red shift. And here we have a purple line that might start to transition into blue from this red shift. So that is what a galaxy that's moving away from us would look like. All the same lines, same relative distance to each other, but red shifted slightly towards the long wavelength side of the spectrum. Same thing's true with blue shifted. If the object's moving towards us, we collect the light, we diffract it, we get the emission lines, and then we compare it to what we see in the laboratory. And you can see on the blue shifted one, all the lines have moved now to the left, to the blue short wavelength side of the spectrum. So where these lines were purple, they become more purple there. Where this line was red, maybe it becomes orange over here. So that would be blue shifted moving towards us. This would be red shifted moving away from us. And this unshifted is when we just look at it standing still. So here's the $1,000,000 question. Given what you know about the Big Bang Theory, the three things that it says, just as a recap, that the universe had a beginning and therefore has an age. The universe started small and has been expanding since, and that over time, energy is spread out, the universe is cooled, and structures have formed like atoms, stars, galaxies, planets, life. Given what we know about the Big Bang Theory, do you think most galaxies in the universe have blue shifted, moving towards us, or red shifted, moving away from us, emission spectra? It's a 50-50 shot. Think about it. If you said red shifted, you're right. And if you knew that, either because of what you know about the Big Bang Theory or because of the title of this video, good job. So who figured this all out? Edwin Hubble. You've probably heard of him, or at least you've heard of his telescope, the Hubble telescope. Edwin Hubble, in circa 1912, was studying the emission spectra coming off of distant galaxies outside the Milky Way by collecting the light in his telescope, diffracting it, and looking at the lines at the peaks. And again, an important piece I want to stress here is he's looking at distant galaxies. He's not looking at stars within the Milky Way. We're talking about looking over much larger distances. We're talking about intergalactic, looking outside of the galaxy at other galaxies far, far away. And what did Edwin Hubble find out? He found that nearly all galaxies in the universe, with the exception of a few in our local group, have red-shifted emission spectra. And given what they knew about the Doppler effect at that time, what we still know about the Doppler effect, we can make the conclusion that if most of the galaxies have red-shifted emission spectra, that means everything is moving away from us. I'm going to pause on this and come back to one point here. There is our local group, which is a collection of a few dozen galaxies. We are close enough together. That local group is close enough together that gravity is taking over dark energy, and the local group is being pulled together. And I don't know the exact number off the top of my head, but in some tens of billions of years, the Milky Way galaxy and the Andromeda galaxy will actually collide. And that collision is happening because of gravity. So on the small scale, we say that gravity wins in this war of forces. But on the very, very large scale, we say that dark energy is causing space and time to spread out. And that's what's pushing everything away. Now, if there wasn't this expansion of the universe, you might assume that it would be about 50-50. That about half the galaxies would be red-shifted, moving towards us, and half the galaxies would be blue-shifted. Oh, I got that backwards. Half the galaxies would be blue-shifted, moving towards us, and half the galaxies would be red-shifted, moving away from us. You might think it would be 50-50 because of just random chance, random motion. But here we're seeing pretty much everything in the universe is moving away from us. So the next point here is why? Why is everything moving away from us? It's because of, and I just hinted on this, that space in between galaxies is expanding. The space itself is getting larger. And when you take two galaxies and you increase the space in between them, the net result is pushing them apart. The way I would like to think of this, or a metaphor that I like to make with this, is take a balloon and put two black dots on it to represent two galaxies with a marker. And if you take that balloon and you blow it up, as the balloon inflates, you're going to start to see those two dots being pushed away from each other. They're not actually being pushed. It's just that the material in between, in this case space, is getting bigger. Another common metaphor would be to think of it like making a, let's say, raisin banana bread. The raisins could be galaxies, and the dough itself is space and time. And so you take the banana bread and you throw it in the oven, and as the dough rises, as the bread bakes, those raisins start to get pushed away from each other. That's what we're seeing with pretty much every galaxy in the universe. Everything is moving away from everything else. A couple more points about this. We've studied this a lot since Edwin Hubble first discovered this, and we're working our way through the distant galaxies and charting them, and looking at their emission spectra. And we know that with the Doppler effect, the faster something's moving, the more red shift or blue shift you're going to see. So the faster it's moving away from you, the more red shift you see. The faster it's moving towards you, the more blue shift you're going to see. And so the farther away a galaxy is, we've found out, the more space in between us and that galaxy, the faster it is moving away from us, the more red shifted the emission spectra. So again, let's say this is some element, doesn't look like hydrogen again, but some element's emission spectra, the laboratory reference is at a standstill, the object's not moving. Like a star in a nearby galaxy might be a little red shifted, so that this purple line becomes blue and this yellow line becomes orange. And then a nearby galaxy might be more significantly shifted to the red side, so this purple line becomes a deeper blue. This blue line's going into green now. And then as we move out to more distant galaxies, we can see the shift. If we were to just follow this thick black line up, we can see the shift increasing so much to the point where this very distant galaxy, if I looked at this line right here and I tried to follow it up, notice how that line has disappeared from the visible spectrum. Remember that light is a spectrum far bigger than just visible light. So this line has actually been red shifted into infrared light and would no longer be visible to us because of how fast that object is moving away from us. All right, and so the last piece is we're actually going to come back to cosmic microwave background radiation just for a moment, since you know about the Doppler effect. And this is just kind of like a cool, fun bonus. Recall that the cosmic microwave background radiation, the CMBR, is the leftover glow of the early universe that we see when we look out to the edge of our observable universe. So it's the glow of the baby universe when we look out as far as we can possibly look, because that is what the speed of light limits us to. You might have wondered, why is it microwave? That light, when it was produced, was visible light that filled the entire universe, similar to the way that light fills the sun. So in the beginning, the universe was this kind of like orange color because the heat, the energy was so concentrated. So it was visible light in the beginning, in the Big Bang. So what's happened since then? Well, since the beginning, the edge of the universe has been moving away from us. By the expansion of universe, the edge of our observable universe, this wall that represents the cosmic microwave background, has been pushed away, just like two galaxies are pushed away because space in between is getting stretched. Um, so since the edge of the universe is moving away from us, what's going to happen to that visible light? The visible light from the CMBR has been redshifted through the Doppler effect, has been redshifted all the way to the microwave portion of the electromagnetic spectrum. And the CMBR is actually going to be the most redshifted light in the entire universe. And with that, I think that's going to conclude our last assignment on the Big Bang Theory, or our last video on the Big Bang Theory. You'll have one more assignment with it on Thursday. My wife wants you to see DJ as a reward for making it to the end of this video. This has been one of the longer ones. Let me grab Verna. And, we're just like vibing in here. So I hope you guys are vibing at home. And we will see you around soon. Bye, guys.